All right, your non-resident training course, September 1998. Navy Electricity Electronic Training Series, Module 13, Introduction to Number System and the Logic, NAVEDTRA 14185. This was distribution statement approved for public release distribution unlimited. 83. Chapter 2, Fundamental Logic Circuits. Learning objectives. Upon completion, the instructor should be able to do the following. Identify the general logic, condition, logic state, logic level, the positive and negative logic as determine the characters apply the input-output fundamental logic circuit. Identify the following logic circuit gates, interpret the solve the associated truth table and or inverters, non-circuit, and a negative and negative or. Identify various operations for the fundamental logic gate for the interpret the associated truth table to determine the output expression, logic gates, in combination, recognize the laws and theories and purposes of the Boolean Algebra. Introduction. In Chapter 1, you learn with the two digits of the binary system will be represented with the state of the condition of the electrical electronic device. The binary 1 can be represented by a switch, which is closed with a lamp that is lit with the transistor is conducting. Conversely, the binary 0 would be represented with the same device, opposite state, and switch open, lamp off, with the transistor cut off. In this chapter, you will study 4 basic logic gates that make up the foundation of the digital equipment. You will see with the type of the logic that the equipment that accomplishes with the desired result of the chapter include the introduction of Boolean Algebra to logic mathematics system. You for the digital equipment that certain Boolean expressions are you for the explanation of the basic logic gates and their expressions will be used with each logic gate is introduced. Computer logic. Logic is defined with the science of the reasoning. In other words, the development of the reasonable or logical conclusion based on unknown information. Or your general logic. Consider the following example. If it is true that all Navy ships are gray, and then the U.S. Lincoln is in Navy ship, that you would reach the logical conclusion that the U.S. Lincoln is gray. To reach logical conclusions, you must also, with the qualifying statement, the condition of the truth, for each of the statement that there is a corresponding false condition. The statement that U.S. Lincoln is Navy ship is true, therefore the statement of the U.S. Lincoln is not a Navy ship, that is false, therefore in between conditions. And the computer operated with the principal logic of the true and false logic conditions of the logic statement to make program decisions. Alright, the condition of the statement that can be represented by the symbol of the variables for the answer for the statement that today is payday, but may be represented by the symbol of P. If the today actually is payday, then P is true. If the today is not payday, then P is false. As you can see, the statement of the two conditions of the computer of these two conditions represented with the electronic circuit operating with the two logic states. These logic states are 0 and 1. Respectively, 0 and 1 represent the false and true conditions of this statement. When a true or false conditions are converted with electronical signal, they refer to as the logical level is also called high and low. The one state might represented by the presence of an electronical signal high, while the 0 state might be represented absent of the electronical signal low. If the statement that today is payday is false, then the statement that today is not payday will become the true. But this is called the complement. The original statement in this case for the computer math complement that defined with the opposite of the negative form of the original statement. The variable if the today were payday, then the statement that would, today is not payday would be false. The complement shown with the place in the bar as or a vinculum over the statement symbol is in this case p underslash or division a score over top of the p. The variable spoken as not p. Table 2 will show the concept relation for the logic state for the logic levels. Our relationship to digital logical concept terms. The statement, the original today is payday, symbol P, that is true. The conditional logic state is 1, logic level high. To complement today is not payday, overstatement the P, vinculum, if the condition is false, the logic state is 0 low. Original example 2, today is not payday. Original today is not payday. P would be the symbol that would be false, and 0 or 1 low. The complement today is not payday. Overscore P true and logic state 1 high. In some cases, more than one variable, even the single expression. For example, the expression A, B with a C overscore C is and D is E, as is A and B and not C and D. Positive and negative logic. To this point, we have been dealing with the one type of logic polarity. Positive. Let's further define logic polarity, expand the cover to the more detailed difference between the positive and negative logic. Logic polarity is type of the voltage with the U for the representative of the logic state with the over the statement that we have to determine the two logic states that can be represented with electronic signal within two distinct voltages. Maybe for instance, the positive voltage can be represented with number one state. Negative voltage can represent the 0 state. The opposite is also true. Logic circuits are generally divided into two broad classes according to their polarity: positive for the logic, negative for the logic. The voltage for the U for the need of the statement, indicating the U for the positive and the negative logic will usually specify the logic diagram supplied by the manufacturer. In practice, many variations of the logic polarity, U for, for example, the high positive, the lower positive the voltage, from positive to the ground, from the high negative to the low negative voltage, and from negative to the ground. Brief description of the two general classes of the logic polarity are presented in the following paragraphs. All right, positive logic is defined as solved if the signal is active with a circuit of the one state of the voltage level is more positive than the zero state of the logic polarity is considered to be positive. The table 2 show the manner in which the positive logic may be used. Example 1: active signal with a true 1 high 10 volts. Component false 0 low 0 volts. Active signal true 1 high 0 volts. Complement false 0 low 10 negative 10 volts. As you can see, the positive logic one state with a more positive voltage less than level than zero state. The negative volt logic. As you might suspect, negative logic opposite of the positive logic of the defined as follows: if the signal is activated, if the circuit is the one state, the voltage level is more negative than the zero state of the logic polarity is considered the negative. The table 2 show the manner of the negative logic may be used. Alright, example 2, the negative logic active signal true 1 low voltage 5 volts, complement false with 0.5 and positive 10 volts, active signal true 1 low volts negative 10 volts, complement false 0.5 negative 5 volts. Alright, note that the low logic level is now represented with the 1 state, with the state 1 voltage is more negative than the 0 state. With the example to show with the negative logic, that you know that the voltage for the logic of the 1 state is more negative than the respect of the logic 0 state. With the whole of the true, but example where both voltages are positive. In this case, they may be easier for you to think of the true condition of this being left as positive than in false condition, either the way the end result of the negative logic. Even the positive and negative logic, the digital equipment is a choice that will be made by a design engineer with a difficult technical and in this area limited understanding type of the logic being with you keeping it in mind with the troubleshooting. Alright, no, unless otherwise noted, the remainder of this book will deal with only with the positive logic input, the outputs, the stable logic input, circle with the U will vary the symbol of the variables, U with the represent of the inputs and output, the purpose of these symbols is let you know with the inputs of the required the desired outputs. If the symbol A is shown with the input of the logic device, the logic level represented with the A must be the high to active of the logic device. They must satisfy with the input requirements required with the logic device before the logic device will issue the true output. Locally, look at view A with the figure 211 and symbol the X with the representative of the input. As long as the switch is open, the lamp does not lit with the open switch represented the logic state 0, but therefore of X. So X is equal to X is equal to 0. When the switch is open, when closing the switch view B represents the logic state with the X, closing the switch completes the entire circuit with the lamp circuit with the then state with the X is satisfied with the input requirement of the circuit, therefore to produce the desired output. Logic high with the current will be applied with the lamp, causing it to light. If you consider the lamp as the output, logic device for the same conditions. If the true with the number to one state, the output of the logic device have the lamp lit with the lamp is not lit with the output of the logic device is false 0 state. With the state of the logic circuit, it's important you remember the state that 1 or 0 for the inputs of the output. So far as the chapter, you've discovered the two condition logic statement, the logic state the represent with the two condition logic level, the associated electronic signal, the positive, the negative, the logic with where you're now ready to produce. See the individual logic device operations. These cover the majority of the computer circuit. Each of the as each of the logic devices are presented with a chart of the call for the truth table that will be used to illustrate as possible input with the corresponding output combination. The truth table is particularly helpful in understanding the logic device, showing the difference between the device and logic operation. We'll start with the chapter for the and or not, or in NAD and NAR, or not negative, not an and not an or. The device accomplish an operation with the logic gate with the more information with the gate for the gates or for the foundation of the digital equipment that they are decision make with the circuit of the computers of the type of the digital equipment to make the decision. We mean with a certain condition must exist to produce the desired output. In studying each gate, you will introduce the various mathematical symbols known as the Boolean Algebra expression. The expressions are nothing more than a description of the input of the requirements necessary to activate the circuit with the resultant circuit output. The AND gate. The AND gate is logical and requires that all inputs to be true, but at the same time, in order for the output to be true. Logic symbol. The same with the symbol of the AND gate that is shown with the figure 2. The variation from the same symbol that may be encountered with the variation may be necessary to illustrate the AND gate and may have more than one input. Figure 2 show the AND gate. In two variables, the A and B with the inputs for the AND gate with the both A and B would have to be true, but at the same time to produce the desired true output. The symbol F is designated for the output function. The Boolean expression for the operation F is equal to A times B, or F is equal to A and B with the expression and the expression F is equal to A and B. The dot lack indicates the AND function. the AND gate operation. We can demonstrate the operating with the AND gate with a simple circle with a 2 switch with a series shown with figure 2-3. You can see that both the switches would have to be closed at the same time with the light of the lamp. The AND view A with any other combination switch position view B would result in an open circle with the lamp would not light logic 0. Now look at figure 2-4 with the signal A with applied with the one out input with the over the AND gate and the signal B with the AND to the other. The time is interval 0 with the both inputs of the logic low, logic 0, and F is equal to low at the time interval 1 with the high logic 1 with the B remains low with as a result of the frequency remains low with at the time interval 2 low as A goes low and B goes high. Frequency, however, still stays low because the power input conditions have not been satisfied. A and B both at high at the same time in the time interval 4. Both A and B are high as a result. The frequency is high, but the input requirements have been satisfied as output with a high logic 1. Alright, 2 and 4 show the AND gate input and output signals logic with A and B, time interval 0, 1, 2, and 3, and 4, and 5. H, high, A and B, frequency in A equals B. The truth table. Now let's refer to the figure 2-5 with this. You can see with the truth table, the table, the combination shown with the letter of the deviation, truth table, the high and low logic level to depict the gate with the input with the resonant output with the combination rather than 1 and 0 logic and state with the big 4 input with the output with the two tables. You can see how they easily converted to the other. Remember, the 1 is high and the 0 is low, but the two combinations showing that only familiarize you with existence and will not be seen again with this book. As you mentioned earlier, with the truth table, the shows that all possible the combination input, the resulting output compared, and the AND gate, the truth table within the input figure shown in figure in 4b. Alright, 2-5 show the AND gate logic for the truth table, the table combinations. Notice A, B, 0, 0, 0, show for the low, 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 0, 1, 0, show for the low, high, low, 1, 0, 0, high, low, low, and 1, 1, 1, high, 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 table combinations. First combination for the A is equal to 0, B is equal to 0, corresponding with the table 0 with the figure 2-4 with the second the table time interval 1 with the third time interval 2 with the last time interval 4 with the control for the truth table the most include with all the possible combinations of the inputs include the all 0 combinations. Truth represented with the AND gate with the 3 input for the X, Y, and Z. With shown below, remember the two inputs for the AND has the 4 possible combinations only of those combinations provide the high input for the AND the gate. 3 inputs for the 8 possible combinations. Again, with the only combination provided with the high output, and they should include all the possible combinations of the check with all the public have all the combination rate of the 2 with the power equal to the number of the input variables. This will give you the total number of the possible combinations. For example, the example of 1 A, B is equal to 2 times 2, the 4 combinations X, Y, Z, 2, the third 8 combinations. Alright, as with AND gate, the inputs must be high with the same type of the produce with the high output, but becomes U with the complement of the variable, the U with the input of the complement indicate with the input, and to the AND gate, they must also have the high, it must also be high to satisfy the input requirements for the gate. Boolean expressing the output formulated based on the true input, but given them with the true output, but he is able to adage might be helpful to be better understanding the AND gate. In order to produce the one output with all the inputs, it must be 1. If any with all if any or all the inputs are 0, then the output will be 0. For the following example, help you remember the concept of the your reminder. Remember the inputs where the original variable of the complement must be higher in order to for the output to be higher. With the 3 examples of the given and all gates are in 2 inputs. To keep in mind with the Boolean expression for the output is a result of the inputs being high. 2-5 show the AND gate with the 2 inputs of the truth table. You will soon be able to recognize the truth table for the other type of the logic gates without having to look at the logic symbol. The OR gate. The OR gate difference with the AND gate is only one input, but they have the high produce the high output. The easy way to remember the OR gate is that the high input will yield the high output. Logic symbol. The figure 2-6 show the same symbol of the OR gate. Remember the inputs will be according to the need of the designer. The OR gate show that is like input is a concave in wall. OR gate may also be represented in a sample of a circle that is shown by the 2 of the OR gate with the 2 switches for the parallel of the other parallel circle switches are closed. The U with the lamp light will only light with the lamp will not light with the be lit when both switches are open. View B. Let's assume that we are applying 2 variables x and y with the input for the OR gate with the circle that produce for the high output for the either x and y, but both must be high. The Boolean expression for the operation is the frequency that equal to x plus y, or the x is equal to f is equal to x or y. The plus indicate with the OR function, but this should not be confused with an addition. The OR gate operation. Look at the figure 2-8 with the show that at the time interval 0 with both x and y are low, with the F frequency is low, but at the time 1 x goes high, with the produce the high output, with the terminal 2 both the inputs go low, but the frequency goes low. When y goes high, the timing 3, the frequency also goes high, remains high until the both inputs are low, again low. Time interval 5, both x and y go high, and causing the frequency to go high. Figure 2-8 shows your OR input-output signals, time interval 0, 1, 2, 3, 4, 5, 6, X, Y, Z. Alright, your truth table. You have the input with the X and Y, but let's construct with the truth table for the OR gate that you can see from the discussion. Figure 2-8, but there are 4 combinations for the input, at least each of the combination for the input with the receiving outputs. You have the truth table for the OR gate. Frequency is equal to X times Y. When writing the stating of the Boolean expression for the OR gate with more than 2 inputs, simply with the play for the OR sign with the positive input, read the with the sign with the OR. For example, the Boolean expression for the OR gate with the input for the A, B, C, and D will be frequency of the A plus B plus C plus D. For expression spoken with the F equals A or B or C or D. You can substitute the complement the original statement that we did with the AND gate and use the negative logic, but for the AND output from an OR gate, at least one of the inputs must be true. Alright, the inverter. The inverter, often referred to as the NOT gate with the logic device with the output opposite of the input, but then sometimes with the called the negator. Must be alone with a combination of the other logical device fulfillment and equipment requirement. The inverter will be achieved alone with a representative with a symbol shown in figure 2-9, view A, with the will more often be seen with the conjunction with the symbol of the amplifier, view B, with the symbol of the inverter sheath. Combination with other devices will be shown later in this chapter. A and B. Inverter A shows as a symbol of the used alone, and B is a symbol of the amplifier inverter. Look at the back statement of the today's today. We state with the P represent with the true state. If we apply with the P, the invert shown with your 210 with the output with the opposite with the input with the output with the in this case with the case with the over the positive at the time interval 2 with the time interval 2 the power on the P is low. The constantly output with the P over the P is high at the time interval 2. P goes high and the result with the overscore P goes low. Remaining the overscore P remains low with the along into the P is high and vice versa. The Boolean expression output with the gate is equal to F equals over slash P. So figure 210 shows the inverter input resonant output. Once again, B was a symbol of the amplifier inverter. A was an inverter used alone. So you have an amplifier inverter. Frequency is the P over P. We recall that the overscript P with the complement is P, but the truth table to invert with is shown below. The P is equal to 0, F is equal to 1, P is equal to 1, F is equal to 0. Output with the inverter will be complement with the input with the following examples show the various input with the inverter's resulting outputs. ABC with the show the overscore ABC, X plus Y, X plus overscore X plus Y, RS over in through the inverter would be RS. The Vinicum non-sign display over the entire output removed from the output depending on the input. When you apply the A overscore B to see the input for inverter, the output would be overscore A overscore double overscore B overscore C. If you run the output through another inverter, the output would be A overscore B plus C. All right, the N and gate. The N and gate is another logic device commonly found with a digital equipment. The gate is assembly as simple as an AND gate with an inverter NOT gate at the output. Logical system. The NOT and AND gate is shown in figure 211. This is the 211 show with the NOT and AND gate. The NOT and AND gate have 2 or more inputs. The output will be low and only when the inputs are very high. Conversely, the output will be high when any and all the inputs are low. The NOT and AND gate can perform the 2 function AND and NOT, separating the NOT and AND symbol to show that the 2 function that would reveal the equivalent circuit depicted with the figure 212, which should help you better understand the NOT and AND gate functions. Figure 212 shows the NOT and AND gate equivalent circuit that either X or Y or both are low, or both X and Y are high. Okay, inputs X and Y are applied with the AND gate to the AND gate with either X or Y are both low. In the view A, with the output of the AND gate with the go below the low logic of the 0, the input of the inverter resulted in high logic 1. Output both X and Y are high. The view B with the output of the AND gate with the high with the output with the inverter low. The Boolean expression output and not in the AND gate with the these input with the frequency of the equals overscore X and Y. The expression is spoken as or vinicum X and Y. The expression of X and Y quantity not for the output with the not an AND gate with the negation input with example for the input with the X and vinicum Y. The output would be X vinicum and double vinicum Y. Now, not an AND gate operation. Now let's prove for the logic level of the corresponding output shown in figure 213 at the time of the time interval 0 with the X and Y with the both low, the output with the high, the opposite with the AND and the gate with the same input at the time interval 1, X goes high, but the Y remains low with the result of the output with the high. At time interval 2, the X goes low and Y goes high. Again, the output remains high, but both X and Y are high. And the time interval 4, the output goes low, and the output will remain low only as long as the X and both are high. Our figure 213 show the not an AND gate input and output signals, X and Y and frequency. Show the X and Y with the gate and the inverter. A regular gate and an inverter. Truth and table. The truth table is not an AND gate with the X and Y inputs that's shown below. All right. F is equal to the vinicum of the X and Y. All right, the not OR gate. As you might expect with the not OR gate, is an OR gate with the inverter on the output. All right, logic symbol. The standard logic state with the gate shown in figure 214. Most of these two inputs may be shown. You have your OR gate with the inverter. The NOR gate will have the not OR gate will have the high output only when the inputs are low. When broken down with the two functions performed in the not OR gate, can be represented with the equivalent. The circuit is depicted with the figure 215 with the both inputs for the OR gate with the low, with the outputs for the low applied with the inverter gives a high output. If either both of the inputs are OR gate or high, the output will be high. This high output is applied with to the inverter, resulting in the output is low. The Boolean expression for the output of the not OR gate is frequency equals the vinicum of the X plus L. The expression is spoken as X or L quantity not. 215 not OR gate equivalent X or L would be equivalent to not. The NOR gate operation logic level is corresponding with the output with the negative. Notice that it has the not OR gate plus the amplifier inverter logic level. The input and corresponding out of the not OR gate with the shown figure 216 at the time of the time interval 0. Both X and L are low as a result of the frequency is high at the time interval 1. K goes high, low L remains low. The F gate goes low. The time interval K goes low, the L goes high, the output remains low, the output goes high again at the time interval 3. Both inputs are low, the time interval both inputs are high, the output goes low, the remaining low units until time interval 5. Both inputs go low. Remember, the output is just output. Would it be farther than an OR gate? All right, figure 216 show the not OR gate input output signals. Truth table, the not OR gate with the X and L inputs are shown. Frequency is equal to vinicum of the X plus L. All right, variations of a fundamental gate. Now, note that now that you're familiar with the fundamental logic gate, let's see some of the variations of these gates that you may encounter. Upon noting, up to now, you have seen the inverters used alone with on the output of the AND OR gate. The inverters may also be used with one or more inputs of the logic gate. Take the logic. Look at the example to discuss the following paragraphs and or not AND gate variations. And play for the inverter 1 point with the 2-input AND gate with the output will be quite different from the same with the AND gate. With the figure 217 will play for the inverter with the A input with the A is high, the inverter makes it low, the gain going into the AND gate, and in order to the output to be high, it would have to be low while B is high, as shown in the tribute table of the inverter, whereby B is input with the output expression would be the frequency of the A is equal to the frequency A times the frequency A B vinicum. Alright, now let's compare with the, not AND gate with the AND to the AND gate with the inverter with each with the input figure 218 show with these gate with the associated with the truth table of not AND gate with the view A output is high with either both of the inputs are low with the AND gate with the inverters each with the view B with the produce the high output with both the inputs that are low with the comparison also point with the difference between the expression of the frequency is equal to A and the vinicum B with the A and B with the quantity not, and the frequency is equal to the resultant of the vinicum A and vinicum B, not A and not B. Now look over the truth table of figure 217, 218 219, look at how the outputs vary with the inverter's differential position. View A, AB frequency, Vinicum A and B with the AB frequency, Vinicum A, Vinicum B. A comparison of the not AND gate with inverter play, input with the A and not AND gate B and the AND gate with inverters out on each input. A and B frequency, inverter, Vinicum A with a double Vinicum inverter B, and or gate variations. The outputs of OR and not OR gates may also be chained with the U for the inverters and OR gate, and one input with the inverter with the shown with the figure 220 with the output of the OR gate requires that low to be high. Both of these conditions exist at the same time in order with the high output. Since the input inverted with the both must be low, B is low in order to produce the high output. Therefore, the output is frequency of the Vinicum A plus B. All right, so you have the inverter on the A and B and the frequency of the Vinicum A and plus B. I figured 224.1 should compare for the not OR gate view A with the to an OR gate with the inverters, both of the inputs for the view B with the show with the respect of the truth table to the not OR gate with the will produce the high output only when they both inputs are low with the OR gate will the inverter produce high output while all in combination except with the both inputs are high. The figure illustrates the difference between the expression of the frequency of the Vinicum is A and plus B and or B equality not, or frequency of Vinicum A plus Vinicum B or not A or not B. Alright, as with the not AND gate, with the more input with the not OR gate, it must be inverted. Figure 220 show that the resulting inverting with the not OR gate, in this case, with the inversion with the B input with the inversion output, with the only time with the gate will be due for the high output with the A low and B is high, with the output Boolean expression of the gate. If the frequency F is equal to the Vinicum of A plus the double Vinicum of B shown with the AND or not B quantity not. Figure 223 for the not OR gate with one inverted input. Two tables 2-4 show the AND or not OR not AND or and OR gate combination produce for the same output. You can see the table sees more the one way to achieve the desired output. All these gates that have only two outputs, so have only two inputs. The table can be extended to more than two inputs. And the equivalent should be the and not or not and or gates. Figure and or gates, not and gates, or gates, A and B and F. Alright, logic gates and combination. When you look with the logic circuit diagram of the digital equipment, you now are going to see the single gate with the most combination for the gate of the first scene, with the confusion for the complex for the interpret the one with the gate at the time that you may work with the way through a networking section. You will analyze the shuffle the combination for the gate and then provide with some of the practical problem. Figure 223 view A show with the simple combination for the AND gate with the output of the gates 1 and 2 with the input for the gate 3, where they already know that the both inputs for the AND gates must go high at the same time in order to produce the high output. Shows, alright, so, you'd have, RS, T, and V, one in RS and T and V, and then RS, T, and V, RS and T and V, 1 and 2, or in 3 with the RS plus T, V, logic combination A is a simple combination of AND gates, and also simple combination of AND gates and OR gates, The output Boolean expression of the gate is RS. The output expression of the gate 2 with the TV. These two, the output expression become the input of the gate 3. Remember, the output Boolean expression is the result of the input of the in this case of the RS and TV spoke with the quantity of the R and S and quantity T and V. In view B, we change the gate 3 to an OR gate, which 1 and 2 remain with the same with the output of the gate that's changed, but we would expect with the output gate is known as the RS plus TV, spoken as the quantity R and S or the quantity of T and V. Figure 2.424 view A, the output of the two OR gates are applied with the input of the third OR gate, with the output of the gates are 1 R plus S, and the output of the gate 2 with the B, T, and V. This input of the output expression with the gate and the RS plus T, RS plus S, and plus T, V, and V. So you have RS and your OR gate with the RS on TV, and second OR gate with the RS, and a third gate RS plus T, TV, RS TV 1 and 2, RS T and V, RS plus T and V, and 3 with RS Vinicum T inverted R S T in the AND gate, and V and Vinicum and V through the amplifier inverted with the V. So you'd have the AND OR gate amplifier R plus STV. All right, C is the output expression in the parentheses without parentheses. Simple combination, a combination of the OR gates. B with this combination of OR gates and gates. C the output expression without the parentheses. All right, and view B, the gate 3 has been chained with the AND gate with the output of the gates 1 and 2, not chained with the cup of the input output of the expression gate 3. In this case, the gate 3 output expression the RS times T and V. This T plus V with the expression spoke with the quantity R and S and or quantity of T or V. The parenthesis of the U with the separator of the input. The terms indicate the AND function without the parenthesis of the output expression would read R plus S times T times plus V with which represented the circle of the V with the C with the arrow can see with the not saying the circle is one depicted the V B. This is very important. The Boolean expression may be written and spoken correctly. The truth table of the output expression of the gate 3 with the view B will help you better understand with the output with the setting with the truth table to know if the only time the frequency is high is when logic 1 is either the both R and S and either both T and V are high logic 1. Now let's determine the output expression for the not OR gate with the figure 225 with the right with the output with the gate 1 and 2 with the A and B. Gate 1, gate 2, the vinicum of G and H. Gate 3, X plus Z. So you'd have A, B, G, and H, and the AND, and X, or X and Z, and an OR. Alright, since all three outputs are applied with the gate for the word perceived with this, you will follow the not OR gate with the which separate each of the input with the gate with the OR sign with the positive and play for the vinicum over the entire expression with the output with the expression for the gate is shown as the vinicum of the A times B plus the vinicum of G plus V, G and H plus the X and plus Z. Truth table shown below only for the gate 4. When you're trying to determine the output of the logic statement gates in combination of these, one gate is at the time. All right, Boolean Algebra. Boolean logic. Boolean algebra is called today with the developer, the Englishman, the mathematician George Bowley, the 19th century, with the basis on the concept of the assumption for the most quantities have the two possible conditions, true and false, and the same theory that have been introduced at the beginning of the chapter. Throughout the discussion, fundamental logic gates have been mentioned. The Boolean expressions as Boolean expression, nothing more with a description of the input with the condition necessary to get the desired output of the expression based on the Bowley's law of the theorems. Purpose of the Boolean algebra is finally design engineers the using system. They are able to arrange for the logic gate to accomplish desired task. Boolean algebra is also engineers enable the engineer to achieve the desired output of the use of the few number of the logic gate the sense the space of the weight and the cost of the import factors and the design equipment. You would usually want to use fewer parts as possible. Figure 2 26 view A show of the rather complex series gate through the proper application of the Boolean algebra. The circuit is simplified with a single OR gate with the shown view B with the figure 227 to show the simplification process of the Boolean theorem of to accomplish it. Or you have JK and X and H and or gate Boolean J and Boolean K H and Boolean H double Boolean K and or gate 3 J Boolean J double Boolean K over the Boolean times plus H Boolean times Boolean J. 4 has another input called 4, and then you'd have, this is a logical simplification. A is the complex series of the gates. B is a simplified single and or gate. All right, show the D. Morgan's theorem, the input of the gate of the D. Morgan's theorem, H and J, associative law with commutative law with complementary law of the union, law of the union. The simplification of the gate indicator the output would always be high properly with the function circle with the concept of the high of one input of the gate. With the input of the gate 3 is constant high, but the output of the gate 4 is controlled with the logical level of the other input. L is higher the input required with the gate have been satisfied with the output with the will be low. Conversely, with the L with the low end of the output would be high with the one of the inputs of the gate 5. Effectively, with the gate is acting along as an inverter. All right, 227 of the logic circuit for the simplification process. Law of the theorem, each of the law of the theorem of the Boolean algebra, law of the simple explanation limited below. The law of the identity, the term of the truth of the one part of the expression will be true, and all parts of the expression that A is equal to A or A is equal to A. Cumulative law. In order for the term to be written down, but it does not affect the value of the A times B that is equal to B times A or A plus B plus B plus A. The associative law of the simple equality statement. A distributed to BC is equal to ABC. A plus BC is equal to A plus B to plus C. Independent law, a term and in within self the O red or ed will itself the equivalent term A times A is equal to A or A plus A equal to A. The double negative of the term law term that inverted with twice the equal of the term is the double Vinicum is equal to A. Complementary law. Term and end completed with a zero with the term of the zero and red. Or the term or ed is complements one is a the Vinicum times the Vinicum A is equal to 0 a plus the Vinicum of 0 a plus the Vinicum A is equal to 1 law of the intersection. The term of the and ed is equal to 1 and the term of the equal to and ed with the 0 equal to 0. A times 1 equal to A times 0 is equal to 0. Law of the union. The term O-red will equal to 1 equals 1. With the term or ed will equal to 0. 0 is equal to 0. The term A plus 1 is equal to 1. Or A plus 0 is equal to A. The De Morgan's theorem. The theorem consists of the two parts of the A1, the Vinicum A and B equal to A Vinicum plus V Vinicum and 2 A and B. And the Vinicum A plus V is equal to A Vinicum times V. Look further, 8/7 of the gates in table 2-4. Distributive law. 1. The term and ed with a parenthetical expression with the B and B plus C with the equals for the term of the and ed with each for the term of the parentheses A times B plus C equals A plus times B times plus A times C. The term of the and or red with the parenthetical expression B times C equal the term or ed with each of the term with the parentheses A plus B plus BC equal A plus B times C is equal to A plus B times A times C A plus C. Law of the absorption. Law of the result of the application. Several other law of the A times A plus B and is equal to A plus A times B is equal to A. Law of the common identities. Two statement that A the Vinicum of the A plus B, the A equals AB, A plus the Vinicum of A plus B, the A plus the Vinicum of the A plus B is equal to A plus B are based on the complementary laws. All right, if your law of identity, communicative law, associative law, independent law, double negative law, complementary law, law of the intersection, law of the union, distributive theorem, distributive law, law of absorption, law of the common identifiers. If you wish a more detailed Boolean algebra, you will be suggested the Mathematics Volume 3, Ivy Trod 10073A1. Summary, Chapter 2.